Okay, for now we're gonna look at example 9. We're gonna skip example 8 from the textbook. Example 7, I would recommend you to read that. That's just a review of how how to find the end behavior of polynomial functions as well as the rational functions involving polynomials. But let's take a look at example 9. I think that's more practical. I feel like this much more practical than other examples. Another way to find a limit of something like sine of 1 over x is to use the fact that the limit of a function as x approaches to infinity is equal to the limit of that function at its reciprocal value of x as x approaches 0 from the right side, okay, or left side, depending on what the original intention was, okay. So let me rewrite this here, okay. So limit of f of x as x approaches positive infinity is the same thing as limit of f of 1 over x as x approaches 0 from the right side. And similarly, limit of f of x as x approaches into negative infinity is equal to limit of f of 1 over x as x approaches 0 from the left side. So I'll give you a couple examples to help you understand that. What does that mean? Okay, so though we're not going to prove this, let's see what this means graphically and also with conceptually. Limit of x, for instance, limit of x as you see as x approaches to infinity would then be the same thing as the limit of 1 over x as x approaches to 0 from the right side. So let's take a look at that graphically. Okay. Well, we know this graph. Okay, as your x value is increasing larger and larger for the original function, y equals x, your y value will be increasing as well. Okay, so the domain for the original function, there's no limit to it. Okay, as your x value is getting larger and larger, your y value is also getting larger and larger. Okay, but let's take a look at the reciprocal function of that. Okay, for the reciprocal function, this time we don't care about the x approaching positive infinity, but we care about the x value approaching to 0 from the right side. So as you can see, once again, as the x value is approaching 0, the y value is getting larger and larger. Okay, so you can see that in the end, in either expression, your y value, your limit will be positive infinity in either case. And then you could say the same thing for the limit of x as x approaches negative infinity, as you would with the limit of 1 over x as x approaches 0 from the left side. Okay, let's take a look at another pair of examples just like this. Okay. So let's think about this. So you could find the limit of the cosine of x as the x value approaches infinity. You could say that that's the same thing as the limit of the cosine of 1 over x as x approaches 0 from the right side. And similarly, you could say that the limit of cosine of x as x approaches to negative infinity is equal to the limit of the cosine of 1 over x as x approaches 0 from the left side. In either case, the limit does not exist. So this is not the best example. So let me give you another example. What if you started with this? Let's say you're concerned with finding the limit of cosine of 1 over x as the x value approaches to infinity. Okay, while this is pretty much the same example as this, okay, you see that our argument or the angle that we're using for cosine is 1 over x. But you could still use the same idea. We could take the limit of, okay, instead of the reciprocal of 1 over x, which becomes just x, and then you could change, okay, where your limit is headed, what's x value you're concerned with. Instead of positive infinity, your x is approaching 0 from the right side. So these two are essentially the same question. Okay, so limit of cosine of 1 over x as x approaches positive infinity is equal to limit of cosine of x as x approaches to 0 from the right side. And similarly, you could say that the limit of the cosine of 1 over x as the x value approaches negative infinity is equal to the limit of the cosine of the reciprocal of 1 over x, which is just x, as the x value approaches 0 from the left side. Okay, and then once again, I want to show you graphically that this is true. take a look at this. So the blue graph represents the limit of the cosine of 1 over x, and the red one cosine of x. As as the cosine of 1 over x is approaching positive infinity, you can see that there's a horizontal asymptote. Okay, it's getting closer and closer to 1. So 1 is your limit, okay, for cosine of 1 over x as x is approaching positive infinity. So the actual value for this was 1. And then also, okay, cosine of x as x approaches 0 from the right side, we know that that's 1. Okay, you could even use direct substitution for that, or you could use the graph, or the values near 0 on the right side, so you can see that that matches. Okay, and then similarly for the second pair, for the second equation, for that example, it's also 1 from the left side as well. Okay, so you could use this idea to answer example 9. So let's go back to example 9. Okay, limit of f of x is equal to limit of f of 1 over x. So you could use the fact that the limit of sine of 1 over x is the same thing as the limit of sine of x, as x approaches 0 from the right side. I should emphasize that. Okay, and what is the value for this one? This one we know. Okay, limit of sine of x as x approaches 0 from the right side, your y value will be 0 for that graph. So then by using this fact, we know that the left side, that limit has to be 0 too. Limit of sine of 1 over x has to be 0 as well.